Group 17, Graph Theory. Graph theory is the area of mathematics which studies graphs. A graph can be a representation of many things in the real world, such as electrical circuits, molecules, or databases. Graphs were not formally known as such till 1878, but there is evidence of early ideas about graph theory in 1735 from Leonhard Euler. A basic graph consists of two features. Each point or node on the graph is called a vertex, and each line connecting vertices is called an edge. A weighted graph is a graph that has numbers attached to edges. These numbers can be used to store real-world information, such as distances. A directed graph is a graph where the edges only direct in specific ways. For example, vertex A can reach vertex B through one edge, but vertex B must pass through two edges to reach vertex A. A spanning tree is a subgraph of a graph which includes all the vertices of the original graph. In weighted graphs, the minimal spanning tree is the spanning tree with the lowest total weight. To find the minimal spanning tree, we are able to use Kruskal's algorithm or Prim's algorithm. Kruskal's algorithm involves selecting the lowest weight edge and then the next lowest edge while not forming a cycle. You can do this until you form a spanning tree. Prim's algorithm involves selecting a random vertex and then adding the lowest edge that is connected to the vertex. You then extend a tree by choosing the lowest weight edges. Also note that both Kruskal's and Prim's algorithms are not perfect and may have errors.
Thank you, Harrison. Now on to our first application of graph theory, networking. Networks are often defined by their ability to transmit data in a low amount of time and also their throughput, which is how much data they can transmit per second. An application where these issues would come to light would be in an editor's workflow. Oftentimes, editors work on projects that have multimedia files that are gigabytes large. This means that they require a high throughput network to be productive and not have to wait for the file to stream to their machine. This, of course, can be solved by graph theory, as I will show you now with this example. This graph will be the graph of our network. Our vertexes will stand for routers, the edges will be the hops between each router, and finally, the weighting on each edge will be the latency of each hop. The situation is that we're at router 1 trying to transmit a file to router 4. We want to transmit that file with the lowest latency possible. We've chosen to use Prim's greedy algorithm to try to achieve that. Okay, the fastest hop from router 1 is the hop to router 3. So far, our route is costing us 2 milliseconds. Now, our fastest hop is the one straight to router 4. There we go. We've successfully transmitted our data to router 4 in the lowest amount of time possible with this graph, using Prim's algorithm. Now, this is much faster to use rather than a brute force method, which would be 1 to 2 to 4, 1 to 3 to 2 to 4, etc. Now, we'll go through how the applications of this provide a benefit in the real world. If a patient were to go to a hospital but their patient files were at another location, the staff might not be able to accurately diagnose the patient. These patient files can become very large due to them containing x-rays, CAT scans, etc. A network with a high throughput would be useful in transferring these files, as it would mean the patient would be diagnosed more rapidly. Entertainment is another area that benefits from this application of graph theory. Online games specifically rely on a low latency connection between the players and the server. Without this low latency route, the player's experience would be significantly degraded. Finally, production workflows can be significantly improved by utilizing high throughput, low latency connections to optimize productivity, as this would result in the editor, for example, not having to wait as long for the file to transfer to their computer. Okay now, on to Nick for graph theory's applications in navigation.
A common use of graph theory, which we all use in our everyday lives, is when we are planning a trip. Whether you realize it or not, you are using graph theory to find the shortest distance or time it will take to travel from point A to point B. We can find the optimal route for our travel by looking at a map as a graph and assigning weights to each edge. In the navigation problem, each intersection will become a vertex, and each stretch of road will become the edges. We will use the distance of each road as the weights for our edges. By looking at a map as a graph, we can begin to find our route. For this example, we will be finding our way from the corner of Epping Road and Lane Cove Road to Macquarie University Hospital. Before we can begin finding our path, we must first change our map into a graph. The first step is to find all the intersections, which will become our vertices. Give each vertex a label. We will now add the edges, which are the stretches of road between each intersection. Give each edge a weight based on the distance between each intersection. We are using meters for this example. We can remove the map and we are left with our weighted graph. Now that we have our graph, we can start finding our path. First, we must choose our starting point. We will be starting from vertex A. We will now choose the edge with the least weight, which takes us to B. We now repeat the second step leading us to C, then to F, and finally to G. We have now used Prim's algorithm to find the shortest path from our starting location, vertex A, to our destination, vertex G. If we look at the map again, we can see that we'll be travelling along Lane Cove Road, through the first intersection, turn left onto Talavera Road, straight through the next intersection, and then we'll be arriving at the hospital. The benefits that come from choosing the optimal path include reducing both the cost and the time of the trip. It also has an impact on the environment as less fuel will be burned.